In this video, we're going to take a look at our circuit symbols as well as our IV, or our current voltage, characteristics for our bipolar junction transistors. So let's start by looking at the symbol for our NPN BJT. So as we can see here, we have our three terminals, our base, our collector, and our emitter. And our currents are defined as we saw previously. We have base and collector currents going in and emitter current going out. We have an arrow here on our emitter terminal indicating the direction of the current. So overall, pretty simple circuit diagram. There are typically a couple voltages that will be labeled here that are relevant. So of course, as we talked about, we're interested in our base emitter voltage, so VBE. So we want to make sure that that's high enough to turn on our base emitter junction. And then oftentimes we'll also talk about our collector emitter voltage, VCE. And sometimes we can also label our VBC, but most times we'll just deal with the other two. We'll just have our VCE and our VBE. So that is the diagram for our NPN structure. So we have a similar diagram for our PNP structure. So the only difference here is our current directions. So of course we still have our same three terminals, our base, our collector, and our emitter, except now our base current is coming out, our collector current is coming out, and our emitter current is going into the device. So we see that in accordance with that, the arrow on our emitter terminal is now pointing in towards the BJT. So that's one way that we can easily tell whether a BJT is NPN or PNP, is we just look at what direction that arrow is pointing. And so it's not uncommon to see the PNP diagram sort of flipped vertically, such that the emitter is on top and that arrow is pointing in, but now downward into our transistor, and our collector terminal is on the bottom. Just like with our NPN structure, we'll also often label a couple important voltages. Here we're concerned with our emitter base voltage, V sub EB, and our emitter collector voltage. And so you can kind of see it's a little bit awkward to be drawing these voltages sort of upside down, which again is one reason that oftentimes you'll see this structure sort of flipped such that the emitter is on the top and the collector is on the bottom. Okay, so that's sort of our basic structure. So now what we want to do is we want to consider what does an IV characteristic or a current voltage curve for these devices even look like. So just for reference, of course, we saw for the diode, we said, we're tracking our diode current versus our diode voltage, and we had some exponential curve that looks like this. Well, now we have this three-terminal device, so how can we even determine this IV characteristic? So what we're going to do is we're going to consider a particular circuit first of all. So it's going to change, our IV characteristic might change a little bit or shift a little bit depending on how our circuit is configured. But we're going to look at something called a common emitter circuit. And so the reason this is a common emitter circuit is because our emitter terminal is connected to ground, as we see here. Notice this is similar to some of the basic diagrams we looked at before. We have this VBB, we have this VCC, and so what those are doing is that is biasing our transistor so it can be in various modes. So we've talked about how to bias it to be in forward active mode, but of course as we change those voltage values, the two highlighted values, we can change the operation mode. So what we're going to be interested in plotting is we're going to be interested in plotting this collector current I sub C as a function of this collector emitter voltage V sub CE. And so one thing to note is we could sort of do a pseudo KVL here. So let me label as well my base collector voltage. So we could sort of do a pseudo KVL around this loop here. Again, starting anywhere, going any direction. And we could see that our VCE is equal to VBE minus VBC. And so with that in mind, we could sort of restate a condition for our forward active mode. So we could say for our forward active mode, we need our VCE greater than VBE on. And so this is the first time we're introducing this VBE on terminology, but essentially we can think of this VBE on as being similar to the cut-in voltage, the V gamma for our diode. So typical values on the order of 0.7 volts. So if we have that true, then what that means is that our VBC is going to be 0 or negative. So again, what this is basically saying over here is that our base emitter junction is forward biased and our base collector junction is reverse biased. So just sort of a little different way to look at that. But again, sometimes we won't have that base collector voltage explicitly labeled. So it turns out that what our curve looks like is we have something like this. So we have some slope here, and then at a certain point we'll sort of level off and it looks like this. So now keep in mind we said that ultimately this transistor is behaving like a constant current source. To an extent, it doesn't depend on that base collector voltage just so long as it's reverse bias. So in an ideal transistor curve, what we would see is that this line, this blue line, would be horizontal for some base current IB1 above some value of VCE. In reality, what we're going to see in the next video is that we have some non-ideal effects which change this from being horizontal to actually having some slope. Of course, I've exaggerated it there, and we'll talk about that more in the next video. So this blue curve is for a particular value of our base current IB. Well, we can adjust that base current by changing the value of our VBB. So if we decrease our VBB low enough, well, we won't have any base current because essentially we won't be turning on this base emitter junction. And so that would be this case here where we just have 0 current, so not very interesting. So that would be IB equals 0, which is our cutoff region. So that's if we have a too low base, or sorry, not base voltage, a VBB value that's too low or reverse bias such that we're in the cutoff region. Now, on the other hand, we could of course increase our VBB. And so what we can see is that that is going to increase our IB. If that's not immediately obvious, we're going to talk about that in a couple videos when we look at DC analysis. So increasing VBB will increase our base current. And remember, if we're in our forward active mode, so sort of out here in this region, which again I'll clarify here in a little bit, that means we're going to be increasing our collector current because IC equals beta IB. Again, only in forward active, so only forward active. So what we would end up seeing then is for an increased base current, we're going to get some curve that looks like this. So this would be for some IB2, which is greater than IB1. And so we could keep increasing that, and so I've sort of exaggerated this sort of slope at the start a little too much. But if we increase that, we get another IB3 that's bigger than our IB2. And again, ideally, these are horizontal curves once we get to that sort of flattening out point. So let me go ahead and label our different operation regions. So over here where we have sort of our constant current, that's going to be our forward active mode. And then where all of our curves sort of coincide, this is going to be our saturation mode. And so typically we're not going to be operating our device in the inverse active, so that's why we don't see it showing up in this IV plot. And so because we have different IV curves instead of just one, for example, that we saw for the diode, what we call this is actually a family of curves. So family of curves, and we can get this by varying that VB value. Sorry, the VBB. That DC source that's applied between our base and ground.